Welcome everyone. In this video, we are going to talk about Fourier series, but for some special sort of functions. Okay, right. So the first thing first, if you can recall that if you are given a function which is 2 pi periodic, so essentially it is defined between minus pi and pi, then we can write f of x as this series, which we are going to call as the Fourier series of the function f. Yes, and a naught, an and bn's are given to be these Fourier coefficients, which is in terms of cosines and sines involving f, right? Okay, now let's look at a small observation. See, let's say that I have a function, yes, and before I move on with theory part, a very simple observation. So let g be a even function, yes. So what happens to g in this case? That is g of x equals to g of minus x, right? G can be any function, it's just an even function, yes, and let's just assume that it is integrable. Then you do see that one has this, that minus pi to pi or minus L to L, does not really matter, but since we are doing it for pi to pi, it will work. Minus pi to pi and g of x dx, right? That you can of course check that this is going to be 2 times 0 to pi, yes, and then g of x dx, yes, and this pi is nothing special. You can of course change this pi to L, yes, and the same thing holds. So this is for even one. On the other hand, we also can see, and let's say that we have another function g which is even odd. G is odd. What does that mean? That is g of x equals to minus g of minus x. Okay, then what happens? Then you can see that minus pi to pi g of x dx is going to be 0. Yes, so these are the two observations. If you are not convinced, please check it yourself. Okay, but this is very simple. Check it yourself. Okay, so with these two observation in mind, you see what is happening here is this. Let's say if you have a function f which is a, for now let's just assume it is an even function. So small observation, if f is even, okay, then f of x is equals to f of minus x, yes, and this holds for all x in R. Okay, now if this happens, then let's look at what happens to this coefficient bn's. So now let's say if we want to write down f in terms of the the Fourier series of f, then bn will be 1 to pi and then minus pi to pi f of x sine nx dx, right? Nx dx. Okay, now f is given to be even, so this is an even function, and then you have this sine function which is again going to be an odd function, right? So odd times even function is going to be odd function, so you can see that the integral of this particular thing is going to be 0. So essentially bn will be 0 for all n in n. Clear? So all we are actually left out with, I mean in this case, is essentially the coefficient a naught and an, right? Okay, and similarly, so this is observation 1, yeah, and now a second observation, observation 2, let's see if f is odd. So basically if f of x equals to f of minus x minus of minus x, okay, this holds for all x in R. So this is odd case if f is odd. Now let's look at this. See, let's look at a naught. What happens to a naught? A naught is 1 by 2 pi and then minus pi to pi f of x dx, of course, and this is going to be 0, right? That's what we did. And again, if you check an's, it will be 1 by 2 pi minus pi to pi. See, an is f of x cosine nx. Cosine is a even function, and then f is an odd function, so even times odd, that will be an odd function. Minus pi to pi integral is going to be 0, so an will be f of x cosine nx dx, which is going to be 0. So and this holds for all n in n. So you do realize in this case it's basically these terms which are remaining, Bn terms, right? Okay, so we can simplify this thing. So let's do that then. Now, see, let me put it this way. Maybe a small from first observation. From observations, what we know is this. Okay. Okay. So if f is a even function, f is an even function, then how do you write Fourier series? F of x, you can only talk about this particular term a naught plus summation n cosine nx. Okay, the n equals to 1 to infinity. I hope this is clear. If f is an even function, yes, and how will you remember? See, for even functions, essentially the Fourier series reduces to this cosine part, only the an part. Yes, because cosine is even, in that way you can remember, right? So only the an part. Okay, and where a naught is as usual 1 by 2 pi minus pi to pi f of x dx, and b an is 1 by pi minus pi to pi f of x cosine nx dx. Clear? And you do realize that this holds for all n in n. Okay, and of course the bn parts are going to be 0, so that's not a issue here. So this is the first observation. This is from first observation, right? And from the second observation, we also know, from the second observation, this is first observation, if f is odd, f is an odd function, okay, then f of x, we can write it as, you remember, a n's and a naught is going to be 0 in this case. So basically we are only left out with the n equals to 1 to infinity, the bn part, right? So bn sin nx dx, yeah, where as usual bn's will be 1 by pi minus pi to pi f of x sin nx dx. Yeah, this holds for all n in n. I hope this is clear. See why this is working out like this, because in our case ans are going to be 0. Yeah, and of course you see all of this, whatever I am doing, all of this is true for a arbitrary period L, right? So exactly the same thing happens, a naught b naught becomes 0 in subsequent cases. Okay, so we are not doing that part, but essentially the exact same thing. Yes, fine. Now one small thing, before of course we will do one example here, yeah, but before that, what we are going to do is we are going to look at a small theorem. Okay, theorem, and this theorem is a very, very important theorem. It actually gives you the fact that, it actually says that the Fourier coefficient, yeah, the Fourier coefficient. So let's say you have two functions, right? f1 and f2. Yes, and let's say they are 2 pi periodic. Yeah, both are 2 pi periodic functions. And so what happens to the sum? So basically the Fourier coefficients, what I'm saying is the Fourier coefficients, okay, of a sum f1 plus f2. Yeah, so you have two functions f1 and f2, and essentially you can of course write a Fourier series for f1 and the Fourier series for f2. What I'm trying to say is this: the Fourier coefficients, yeah, are the sum of the corresponding Fourier coefficients of f1 and f2. Okay, the Fourier coefficient of this sum, yes, are the sums of the corresponding okay, Fourier coefficient of f1 and f2. I hope this is very very clear to you. I don't have to prove this thing because basically integral is a linear operator. So essentially you can do this thing. I mean, it's not a big thing to observe, right? You can of course do it. So the corresponding Fourier coefficients of f1 and f2 is it clear? Yeah, so this is the first part, and of course the second part. So this is basically the Fourier vector space part of it. So basically if you take the Fourier coefficients of all you take the all such functions for which the Fourier series is defined, right, of a particular period, and what happens is the Fourier coefficients actually, if you want to talk about it, that actually forms a vector space. So here what happens is the Fourier coefficients, again Fourier coefficients of C times F. Okay, I hope you know how to define this thing. See, okay, we'll do it later. Are C times the Fourier coefficients, C times the Fourier coefficients of F. Coefficients of F. Okay, so you do realize what's happening here. You see how we are defining it. We are defining it like this: f1 and f2, f1 plus f2 acting at x is essentially f1 of x plus f2 of x. Yeah, this is the definition which we are using, and again c times f acting at x is by definition c times f of x. So this holds for all x in R and c in R. Okay, so with this definition this is true. Yes, and the proof is extremely easy. I am definitely, you can do it yourself, so please do it yourself. Okay, the proof. I am not doing this part. This is very very simple. Yes, okay, so let's look at one example of this particular theorem. Yes, where can we use this theorem? Yes, and the application is quite easy actually. Yeah, so what we are going to do is example, and we are going to start with an example which is a very very famous example. It is called the sawtooth wave. So essentially we are looking at a f of x which is x plus pi, clear, and then it is between minus pi, x and pi. Yeah, and of course it is 2 pi periodic. So basically what does this say? X plus 2 pi equals to f of x means it is 2 pi periodic. So what we are doing here is this: see, the function I am defining it between minus pi and pi, right? And then I am saying that the functions record itself after 2 pi. So essentially what we are saying is we are constructing a periodic function like this. If you want to draw such a function, you can easily do that. See, let's say minus pi, pi, and then 2 pi, and it goes on, right? Minus 2 pi. So in this case what happens is